In this lesson, we're going to take a look at how we add vectors when we're not dealing with things that are strictly parallel or anti-parallel. So we're going to be going into 2 dimensions. Now, remember, a vector has both magnitude and direction. And magnitude is the how big or how many or how far, right? That's the number part. And then the direction tells us exactly that. But how do we give direction in 2 dimensions? In 1 dimension, we used positive or negative. But in 2 dimensions, we have to go back to using angles, right? So the direction is given by an angle. Now, you can pick what you want to measure your angle from for whatever's convenient. Or we can do the standard thing, which is a good idea, to say, all right, well, here's the positive x-axis, here's positive y. We measure counterclockwise from positive x, and we call our angle theta. And so when we rotate our angle or our vector through an angle, we measure it from positive x. And we know that the cosine of theta is positive in quadrants 1 and 4. And we know that it is negative in quadrants 2 and 3. Sine of theta is, of course, positive in quadrants 1 and 2. And negative in quadrants 3 and 4. So we do need to be a little bit familiar with sine and cosine in this. We'll look more at that later. For now, I just want to do this visually without doing any kind of mathematics yet. So let's say I have a couple vectors, and I'm going to say vector 1 is 5 meters, and it's at this angle, whatever this angle is. And then I'm going to have another vector. Let's call it vector 2. And vector 2 is straight up, say, 3 meters. And what I want to know is, what's the vector sum of these 2 things? So let's say I walk 5 meters at 30 degrees north of east. That's about what that looks like to me. And then I walk 3 miles or 3 meters straight north. What is my displacement? Well, remember, displacement is distance and direction from start to end. And so these 2 vectors individually tell me how far I walked, but this vector doesn't start where this vector starts, right? This vector, if I walked 5 meters and then 3 meters, would be up here. But this vector is 3 meters north. So it doesn't matter where in the plane I put it, it just matters that its magnitude and direction stays the same. So what that means is I can slide vectors around so that I can visually manipulate them and add them up tip to tail. And so this 5 meter long vector that's right here could also slide down, and I could draw that as long as it stays parallel and the same length. This 5 meter vector and that 5 meter vector are identical. So what this shows me is, here's my initial starting position, here's my final position, and I walked this path, but my displacement is actually the vector sum of those 2 things. It's from here to here. Right? So this is what I call a resultant vector. It's the result of adding 2 vectors together. And we can visually see that by placing our vectors tip to tail. And it doesn't have to be 2 vectors. We can do this for 3 or 4 or 5 or 6 vectors, or as many vectors as we want. So this is visually adding up these vectors by placing them tip to tail, and then we go from the tail of our very first vector to the tip of our very last vector, and that tells us the vector sum. Now, if you were actually doing this for real, you could measure the length of the vector to represent the magnitude, and you could measure the angle with a protractor to give us angle, and then you could actually draw these out using graph paper, straight edge, compass, protractor, and get the vector sum by just measuring your final resultant. Now, there's a couple other ways. This is the tip to tail method, but there's a couple other methods that you can use to add up vectors. So on this one, we actually slide the vectors, and that's okay because it doesn't change their magnitude, it doesn't change their direction, it just moves them on the plane. But if we have vectors, if we want to look at this another way, like let's say I had one object here and somebody was pulling it this way with 20 newtons of force, and somebody was pulling it this way with 30 newtons of force. What's the vector sum? Well, there's a couple ways to go about doing this. We could slide this vector, this 30 newton vector, over and put it there, and then we would see that our vector sum is actually right here. There's our resultant. But when we do that, we actually start to see that we could have slid this vector over as well. It wouldn't have mattered, and it would have been here. And now what I actually have is a parallelogram. And so my parallelogram, I have my 30-degree vector, or my 30 Newton vector, my 30 Newton vector that are parallel to each other, my 20 Newton vector and my 20 Newton vector that are parallel to each other. And so I drew that diagonal from the starting where they originated to where they come, and that gets me my resultant vector again. So this parallelogram method can be helpful if you have vectors that start in the same point and you're trying to visualize what the vector sum is going to be. And so I don't know what the sum of this vector is, but I do know it's probably a little bit more than 30 newtons, and it's going to be a little bit to the left of vertical. And if I wanted to do some math or I wanted to make the measurements, I could get more precise than that. But this is the parallelogram method of adding vectors. It's visual. It allows me to slide these vectors around and see where my final resultant is going to be.